Okay, this is dedicated to understanding the quantum model. We are beginning our spectroscopy lab, and it is imperative that we understand why we're seeing the lines that we see. We mentioned before the lines represent a fingerprint of the elements, and that every single element has a fingerprint that we can detect using spectroscopy. So, this first began with Max Planck, and Max Planck mathematically determined a constant that linked the amount of energy a photon carries with the frequency of its electromagnetic wave. The equation that he derived was E equals h times v. E is the energy, h is Planck's constant, which is 6.62 e to the negative 34 joules per second, and v is radiation frequency. We can measure the energy of a photon using Einstein's equation, E equals hf, which is also equal to h times c divided by lambda. F is the frequency of photon electromagnetic radiation. As you saw in the previous slide, it's sometimes also symbolized with a V on the chemistry side. Be flexible enough to recognize that the V and the F are the exact same thing. C is 3 times 10 to the 8th meters per second, which is the speed of light in a vacuum. So this is the equation and this is the relationship. We mentioned earlier about the black body radiation, that underneath classical theory, just like the classical model of the atom, there was some problems with it. So underneath classical theory, as your heat increases, the intensity would increase and your wavelength of emitted radiation would also increase. So every time you stand next to a Bunsen burner, we should all be cooked to death, basically, is what he said. And since we can stand next to a Bunsen burner and we don't have those issues, obviously that's not the true case there. So his mathematics actually brings that curve back down into the visible spectrum and explains why items that are black bodies like your ring on your ring stand emit a red light that we can see. Photons. We need to take this time to talk about photons. Photons are derived from the Greek word that means light. These particles transmit light. They are carried over space by, in other words, light is carried over space by these photons. Photon is considered to be an elementary particle, and it has its own antiparticle. In quantum mechanics, each photon has a characteristic quantum energy. Einstein is credited with coming up with the proposal that light consists of separate pieces of energy, or particles, also known as photons. Gamma is a symbol for the photons. Photons move at the speed of light, just like we said, it is light carried over space. And a photon has a given frequency which determines the color. Radio technology makes use of that frequency. So I'm going to take this time right now and we're going to reflect back onto your electromagnetic spectrum, which should already be in your testing materials. So radio waves we use for astronomy because they can go further distances out in space and we can get a read back from them to try to figure out where we are in the universe. X-rays we use when we're looking at bones and trying to find fracture marks. Those are going to be increasing frequency, but their wavelength is going to be decreasing. So there's an inverse relationship here. Gamma rays are the largest. They have the most. They increase in frequency the most compared to your radio waves, but they can travel only short distances, which is why we don't use them so much for astronomy. We're going to lean more to radio. But notice the visible spectrum. So we did a spectroscope and you notice that you had those numbers 4, 5, 6, and 7 in there. Well, that's our range, and these are measured in nanometers. And nanometers means 10 to the negative 9th. So you're going to be getting a readout on your spectroscopy, and when you're looking at your light through your spectroscope, you want to make sure those lights, as they start coming in with measurement, are matching up to the frequency they should be. So if you have a violet color, it should end up in the 400 range. If you're looking at a red light, it should be shifted over to the 700. Okay? How atoms emit light. So basically, we're going to have a collision with a moving particle, which excites the atom. This causes the electron to jump to a higher energy level. The electron falls back into its original energy level, releasing the extra energy in the form of a light photon. So, remember that there is a difference between absorption and emission. So, absorption, I have an incoming photon, it's absorbed by the atom, and as it's absorbed, we see a light. When it's emitted, you have an electron that's moving, and if it's moving down, there has a higher energy photon that is emitted. It can also occur if I move to a lower energy photon, it's also emitted. So on absorption, those lines will be black because they're being absorbed by your nucleus. Emission, I will see a black background and light. The light waves, the lines will be lit up. Difference between absorption and emission. Are you seeing the light? Or is the light being absorbed and you're seeing dark lines that represent your readings? So, absorption versus emission again, basically, if I'm looking at an atom in an excited state and I'm bringing in a photon that has a set energy level, which is Planck times the frequency, and those two meet, afterwards, when that atom goes back to a ground state, to its natural state, during emission, I will see that light being given off. It's being emitted. Now, what that means for us, so we mentioned before that the atoms didn't behave as they expected, and so one of the things is they were getting spectral lines, and so the line color determines how much of an energy gap there is. So as you see on this diagram, a red photon that's being emitted is only moving one energy level. It's moving from a 2 to a 1. If you're seeing green, you're moving at least 2 energy levels. And if you see a blue, you're moving the furthest distance. And that's the whole point. So my red light has lower energy. It moves less. My blue light is on the 400 side. It has more. It's going to move a further distance. Also, another note, why are your sunsets red? Your sunsets are red because that's a longer wavelength and it can travel through the atmosphere and get to your eye. During the day, because there's less atmosphere above us, we see blue because that is a faster moving wavelength. That gets to our eye before the red does. Sometimes it helps y'all see that. And just another diagram, so we would be measuring the change that occurs before and after emission. That's what we're interested in because that tells us what's going on. So the scientists have looked into this, and we have the Lyman series, Balmer series, Paschen series. Basically, they were looking at the light being given off by different atoms and trying to justify what it was. The Balmer series is the one that occurs during visible light, and that's the one we look at. Primarily, they looked at hydrogen atom for their test site on that. Just know, as you move up the food chain, there's going to be different series that they look at for spectral lines. This slide is just noting the fact of the matter is, yes, all we see is visible light, but there's also UV and infrared that also occurs. And those you can get emission as well. Electromagnetic spectrum, I'm going to remind you yet again. Notice there were 2 slides of this. You need this in your reference section. You can print one off, but you'll need it because you need to be able to name what each of the sections are, from radio waves all the way down to gamma rays. And the next point right here is this is where we talked about they were having a problem understanding what was going on with the atom, and part of it is because they did not notice quick enough that there is a wave and particle relationship with the atom, so it acts as a particle and also as a wave at the same time. And that is a key thing it's very foundational to our concept here. Bohr examined the hydrogen model, he questioned Rutherford's model, he postulated a strong nuclear force, and he used Planck's idea of quantum. We've already talked about him before, so he's a review. And again, he looked at the hydrogen atom. Hydrogen is the only one that doesn't have a neutron, so it worked pretty well for a certain point. Einstein is noted for the photoelectric effect. Electrons in a metal are held in an energy well. Electrons must absorb at least enough energy to get out of the well in order to become free for the metal. Electrons had to absorb a single photon with a minimum amount of work, known as a work function, and any excess absorbed energy became the free electron's kinetic energy. Louis de Broglie, he related the motion of a particle to the idea of momentum and related Einstein's formula E equals mc squared. There is momentum, which is a wavelength relationship for a photon. So just showing how they interrelated with one another. Here's the final thought. Okay? Classical theory is sort of like a ramp. You can move up and down anywhere you want it to, which is why I thought it should be a continuous spectrum. There should be no reason why it can't be like that. Okay? Quantum is a set of stairs. You have to have the right amount of energy to move up and down. So if you can remember this analogy, you'll get this down, no problem. Okay? So quantum is a set of stairs. You have to have enough energy to move up and down. Classical is a ramp. Quantum is stairs.